Some problems seem just impossible, right? They have this dizzying number of possibilities you could check. But what if the secret to solving them wasn't about more power, but about having a really good memory? Today, we're diving into a super powerful technique called dynamic programming. It's a way to turn these impossible problems into puzzles that are not just solvable, but, well, kind of elegant. And we're going to start with a classic riddle. Okay, picture this. A long line of treasure chests, each one packed with a different amount of gold. Your goal is to walk away with as much treasure as you possibly can. But there's a catch. If you take one chest, a silence alarm goes off, and you can't take the chest right next to it. So you could grab the first and the third, but no way can you grab the first and the second. So the question is, how do you choose? Which chests do you take and which do you skip to make sure your haul is absolutely maximized? This little puzzle right here is our perfect way into this massive idea. All right, so let's take our little treasure hunt and translate it into a more formal, structured problem. So here it is, the official problem we're trying to solve. We're given a list, an array, of positive numbers. Our job is to pick out a selection of those numbers, a subsequence, that gives us the biggest possible sum. And the only rule, the one big constraint, is that we're not allowed to pick two numbers that are right next to each other in that original list. If we can crack this, we'll basically uncover the core secret of dynamic programming. Okay, looking at this table really makes the problem click. Take that first example, 13, 3, 5, 9, 12. The best you can do is to grab the 13, the 5, and the 12. That gives you a total of 30. Now look at that second example. Here, the winning move is to just take two numbers, the 12 and the 17. That gives you 29, which is way better than any other combination you could have picked. This is a perfect illustration that it's not about grabbing the most numbers. It's about grabbing the right ones. So, how in the world do we solve this? Well, our first gut instinct, probably your first instinct too, is to just try everything. Check every single possibility. So let's explore that natural approach. It's simple in theory, but as we're about to see, it has a massive fatal flaw. The most direct way to think about this is using something called recursion. For every single number on our list, we're faced with a simple choice. Do we take it? If we do, we add its value to our running total. But then we have to skip the next number. Or do we skip it? If we skip it, we can just move on and consider the very next number in line. By making these choices over and over and over again, we end up creating this huge branching tree of every possible outcome. And this right here, this visualizes the huge problem with that simple approach. Every single choice we make creates a new branch. To solve the big problem for n items, we have to solve smaller versions of it, like for n-2 items and n-3 items. But look closely. To figure out n-2, we might need to solve for n-5. And you know what? To figure out n-3, we also might need to solve for n-5. We are literally solving the exact same problem multiple times. It is an incredible waste of effort. And that massive inefficiency, it has a name. The amount of work our simple recursive algorithm has to do grows exponentially. For a small list, it's fine. But if you have a list of, say, 100 numbers, the number of calculations becomes, well, it's astronomical. We're talking more calculations than there are atoms in the known universe. It's just not feasible. Yeah, the source material puts it pretty bluntly. We avoid these kinds of algorithms whenever we can. They're just fundamentally impractical for anything but the tiniest problems. So our simple, intuitive solution? It's no-go. We need a better way. We need a hero for our story. And that brings us to the aha moment. What if, instead of calculating the answer to the same little subproblem again and again, we just remembered it? I mean, what if we solved it once, wrote down the answer, and then just looked it up next time? This, right here, is the central, brilliant idea behind dynamic programming. Let's put these two approaches side by side. The recursive way? It's kind of forgetful. It starts with the big problem and works its way down, but it keeps solving the same small problems without even realizing it. The dynamic way, though, is smart. It starts with the absolute smallest, simplest subproblems. It solves each one just once, and it stores the answer in a little lookup table. Then, when it needs to solve a bigger problem, it just looks up the answers to the smaller pieces it's already figured out. Absolutely no wasted work. Okay, enough talk. Talk is cheap, right? Let's actually see how this smart memory approach works in practice. We're going to build our solution from the ground up, one piece at a time. All right, here's our setup. Up top, we have our input list, our treasure chests. We'll call that A. And below it, we have our memory. It's just an empty list for now, and we'll call it B. Our entire goal is to fill in this B array, moving from left to right. Each little box in B is going to store the best possible sum we can get for a subproblem that ends at that exact position. So the rule for filling in each cell in our results array B is actually pretty simple. For any position, let's call it I, we ask ourselves a question. What's better, taking the current number, A sub I, or skipping it? If we skip it, the best score is just whatever the best score was at the previous spot, B sub I minus 1. But if we take A sub I, we have to add its value to the best score from 2 spots back, B sub I minus 2. We just check which of those 2 options gives us a bigger number, and that's what we write down. And voila, here's our completed table. Let's look at how we got that very last value, 36. At the last position, we had a choice. We could skip the last number, which is 7. If we did that, our best sum would just be the previous best sum, 35. Or we could take the 7. If we did that, we'd add it to the best sum from 2 spots ago, which was 29. And 7 plus 29 is 36. So what's bigger, 35 or 36? It's 36, and that's our winner. The final answer for the entire problem is simply that last value in our results table. And the payoff for this approach is just enormous. The recursive method's runtime, it just shoots up. It's like a vertical wall. But our dynamic programming solution, its runtime just grows in a straight, predictable line. If the list is twice as long, it takes about twice as long to solve. This is the difference between a problem being theoretically solvable and one that's actually practically solvable on a real computer. It's a total game changer. So we found the maximum value, 36. That's awesome. But you might be wondering, which treasure chests did we actually pick to get that sum? Well, it turns out our smart memory can help us with that too. The trick is incredibly clever. As we're building our results table, we're going to store one extra piece of information. For every single sum we calculate in our B array, we're also going to make a little note in a new Prev array. And this note is super simple. It just points to the index of the number we used to get here. It's like leaving a trail of breadcrumbs for ourselves to follow later. Okay, here it is, our complete data structure with that new path array at the bottom. To figure out our solution, we just work backward. We start at the very end. We know our best sum, 36, is at index 10. We look at the path array at index 10, and it points us to index 8. That tells us 2 things. The number at index 10 was part of our solution, and the previous step came from index 8. So we jump to index 8 in our path array, and it points us to 5. We keep following these breadcrumbs backward all the way to the start, and it reveals the exact set of numbers we chose to get our perfect sum. So look, we just solved one very specific problem. But the real magic of dynamic programming is that it's not just a one-off solution. It's a general recipe. It's a mental model that you can apply to a whole class of incredibly complex problems. You can actually boil this whole process down to a 4-step recipe. First, just try to find that simple brute force recursive solution. Second, and this is the most important part, notice if that solution is making a ton of calls to the exact same subproblems. If it is, ding, 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 you found a perfect candidate for dynamic programming. Third, create a data structure, like our array, to act as a lookup table to store the answers. And finally, rewrite your solution to build that table from the ground up, using your stored answers to find the final result. And that leaves us with one final thought to chew on. This idea of breaking a giant problem down into smaller, overlapping subproblems and then solving each tiny piece just once is unbelievably versatile. It's used everywhere, from mapping genomes in genetics to financial modeling on Wall Street to how your GPS finds the fastest route. So the real question to ponder is, what other seemingly impossible problems out there could be made simple just by adding a little bit of smart memory?